Hello, this time circuit analysis level 2. First question, what value must the voltage source have? Right, well, we know what the voltage is at this point in the circuit here. It's 1.57 millivolts. We know that current doesn't flow through a voltmeter because the ideal voltmeter has an infinite impedance, so all of this 230 nanoamps must be flowing through this resistor here, which makes the voltage across this resistor here equal to 230 nano times 750. And this must be at a higher potential than this, because current always flows through a resistor from the higher potential point to the lower potential point. So this point here is 0.000175, in other words 172.5 microvolts above that point there. And we know that whatever this voltage source is plus 172.5 microvolts equals 1.57 millivolts. Therefore, the voltage of the voltage source must be 1.57 millivolts minus the voltage across this resistor here, which is just X. Okay, next. Now we need to work out an unknown resistor. Now we know that there's a potential difference of 15 minus 7.1, which is 7.9 volts across this resistor. So the current through that resistor is 2.2 milliamps, because no current can flow down through here, so all of that 2.2 milliamps must be flowing through that resistor. So we know the voltage across that resistor is just 15 minus 7.1, or 7.9, and we know the current through the resistor, 2.2 milli, so we must be able to work out the resistance. It's just the ratio of the voltage to the current by Ohm's law, R equals V over I. Fine. Next up. Okay, this one. Now, we can work out what the voltage at this point here must be, because we know that from here to here is plus 3.9 volts, and from here to here is minus 5.61 volts, because this is telling us that this point in the circuit here is 5.61 volts above that point there. So the voltage across the resistor must be 3.9 minus 5.61, or minus 1.71 volts. If we know the voltage there, then we can work out the current through that resistor. And the current through the resistor would be flowing upwards in this direction, because this point here is at a lower potential than ground. The current through this resistor would be 1.71, the voltage across it, divided by 3K. And that's the current flowing up. Since an ideal voltmeter has an infinite impedance, no current flows through it, so all of that current must be flowing through the current source, which means that is the current that the current source must be set to. I can just set this to Y, which would be the same as saying 0.00057 or 570 microamps. Fine. Next. Okay, right. Here we again use the fact that this is a voltmeter, an ideal voltmeter, with an infinite impedance, which means that no current ever flows through it. So looking at this node in the circuit up here, we've got a total of 8.3 plus 49 microamps flowing away, so there must be a total of 8.3 microamps plus 49 microamps, or 57.3 microamps flowing into that node. It can't flow through the voltmeter because no current flows through an ideal voltmeter, so that current must be flowing through this 1K resistor. That means we could work out the voltage across this 1K resistor. And that would be, in this case, just X, the current, times 1000, the value of the resistor. So the voltage across this resistor would be 0.0573, in other words 57.3 millivolts. Now the current is flowing in this direction into that node, and the current through a resistor flows from the higher potential to the lower potential, so this point here must be 57.3 millivolts above this point here, which means the total voltage difference between here, the bottom, and here, the top, must be 88 millivolts minus 57.3 millivolts. But that's the voltage across the voltmeter, so that's what it would read. Great. Just do one more. Here we're being asked what value the unknown current source must have. Again, this is an ideal ammeter. It has no resistance, so there's no voltage drop across it. This point here is at 110 microvolts, so this point here must be at 110 microvolts as well. And if we know that this point here is at 110 microvolts, we can work out what the current down through this resistor must be. Just 110 microvolts divided by 13K. And that's the current going down here. Now, we know the current flowing into this node is this unknown current source here, and that must be equal to the current flowing down through this resistor, and minus the current flowing through the ammeter. You see the ammeter reads minus 52.5 nanoamps with the arrow this way, which means there's 52.5 nanoamps flowing this way, right to left at the top. So, looking at this node here, the total current flowing in is unknown, but must be equal to the total current flowing out. And the total current flowing out is 110 microvolts divided by 13K, which is flowing down here, plus 52.5 nanoamps, rather, which is flowing through this ammeter. That's it. Most of the level 2 ones are about that difficulty. Slightly harder one here, perhaps, when we've got two current sources, but we know there's no current through the voltmeter, so we can work out the total current going down through that resistor must be 760 nanoamps plus 280 nanoamps, and if we know the total current through the resistor, by Kirchhoff's current law it must be the sum of this one and this one, because there's no current flowing through here, and we know the value of the resistor times 56K, that tells us the potential difference across that resistor there. And if we know the voltage on this side and the voltage on this side, then we can work out what this voltmeter would say. It would just say 5.7 millivolts, which is the voltage on this side, minus the voltage on this side, which I've worked out down here in the X box, so I could just say minus X, and so on. Over to you. Good luck.